So I think because this is the last session, I think we should certainly start with thanking the organizers of this great conference. I think it's, for me at least, it was extremely interesting to see all these different communities working on very similar problems. So I think we should all kind of applaud the organizers. I'm giving this talk because actually I think originally it was planned that Lawrence would give this talk, but he had visa trouble. So I will give my own version of the talk. But certainly most of the things that I know about the mathematical concepts in this talk, I learned from Lawrence Lotens and Clément Delcamp. The topic is something that has not been really covered by any of the Venn diagrams that we have seen, because actually there's also some aspect about computational physics here. Okay, it turns out that if you look at the history of many body physics in the 20th and 21st century, a big drive to kind of understand many body physics has been to try to see how can I simulate many body systems. If you look at the big revolution of things like Wilson, Kenneth Wilson, I understood, like the RG, this was all kind of motivated by how do I simulate, how do I kind of take a certain Hamiltonian or field theory and how can I actually put this on the computer and get numbers out. And the story here is a little bit similar. So by trying to understand how to simulate quantum spin systems, because this turns out to be very relevant for actual experiments, we have been forced to think about generalized symmetries, because these generalized symmetries give us by far the best or the optimal way or the state-of-the-art methods for simulating these things. And actually you can get huge speed-ups by thinking about symmetries in spin chains. So central to this whole story is something that's called tensor networks. So tensor networks are basically can be seen as the building blocks by which you can construct many body wave functions. Okay, so this is actually something like a revolution that started with Affleck, Kennedy, Leap, and Tazaki. So they constructed like a tensor network for giving evidence to the conjectures of Haldane about the gap, the fact that spin one chains were, Heisenberg's spin chains were gapped, and this was followed up by mathematical physicists, Van der Nachtergaele and Werner, who kind of realized that this class of wave functions is very interesting. Then actually Kenneth Wilson and Steve White, who was a student of Kenneth Wilson, took somehow this formalism developed this formalism of NRG and especially DMRG, which can be seen as a variational method within the class of these tensor networks. And then my colleagues Ignacio Sirac and Guy Frey and many other people then developed algorithms that, and not just algorithms, but also kind of a theoretical understanding of why all these things work so well. Why is it possible to basically simulate quantum spin systems without running into the exponential wall that you would usually have if you kind of look at a many-body system. Okay, so there's some kind of a few crucial concepts in this story of tensor networks. So first of all, in this talk, I will restrict myself mainly to quantum spin systems, but actually much of the stories also go to higher dimensions. But turns out that all ground states of gapped spin chain Hamiltonians can efficiently be represented as matrix product states, even in the thermodynamic limit. Okay, so there's basically some breakdown of the exponential wall, and this leads to a huge simplification for studying ground states, okay, because you can actually, instead of kind of looking at a Hamiltonian and trying to understand, okay, what are the properties of the ground state, you can start studying the manifold of these tensor networks, matrix product states for one-dimensional systems, and it turns out that any state on that manifold is actually a ground state of some local Hamiltonian. Any local Hamiltonian that is a gap has a ground state that is represented in this manifold. And so basically these tensors, so basically you reduce the problem of a global problem, like the simulating or kind of representing the whole wave function in terms of some kind of simple Lego blocks that model the entanglement structure. So indeed modeling correlations makes much more sense than modeling the full wave function, because it's all through somehow the entanglement that all correlations are mediated. And actually some very interesting papers that Feynman wrote that already foresaw this kind of development. And built in these tensor networks is that there's some kind of an effective holographic property that allows you to actually simulate and calculate these expectation value with respect to these states in a very efficient way, because you basically map a 1+1 dimensional model for quantum spin systems to a 1+0 dimensional model, which is basically classical StatMech, and therefore you can actually kind of deal with transfer matrices and things like that. So it turns out that this story is actually very interesting. You can also start looking at non-gap systems, what happens at phase transitions, and you can develop kind of completely new ways of dealing with kind of scaling methods and finite entanglement scaling methods, and there's still like lots of developments there. But the thing that is of most interest for the present talk is that these local tensors, these building blocks by which you build up the wave functions, reflect the symmetries of your system, or the symmetries that are broken in your system. And so basically, so even for topological phase of matter, it turns out that by looking at these local kind of tensors by which you build up the whole wave function, by looking at the symmetries, you can detect topological order, you can detect in what phase you are. So basically, there's a systematic way of lifting this Landau paradigm to the generalized Landau paradigm, where you also have to look for much more interesting symmetries that are not reflected in local order parameters. Okay, so very quick word about the computational aspects of these tensor networks. So I will certainly not explain how all these computational methods work, but effectively you have to think about these tensor networks as being methods that live on a manifold. So I have this exponentially large wave Hilbert space, and on this exponentially large Hilbert space, there's a kind of a very small dimensional manifold where all ground states basically live. And it turns out that they form something like a Kähler manifold. So it has both a complex and a symplectic structure, and therefore you can define Poisson brackets. So you reduce the problem of a quantum problem to basically a classical dynamical system that is governed by Poisson bracket evolutions. And then you can start developing algorithms that simulate this effective classical system that is equivalent to the quantum system. And all these different algorithms basically differ by different methods by which you split these differential equations that you get out of these Poisson brackets. But the important thing for this talk is that the computational cost for finding ground states or for doing dynamics is actually related to things like the entanglement. How much entanglement is there in a system? Okay, so it turns out that the faster the eigenvalues of your entanglement spectrum decay, the more efficient and therefore the easier you will be able to simulate your many-body systems. And if the Schmidt coefficients decay fast enough, and you can actually prove, and this follows proofs of Matthew Hastings and many other people, then somehow you can reduce this exponential problem to a polynomial problem. And so, for example, this is the entanglement spectrum. So this is the log of the Schmidt numbers of a bipartition of your quantum spin chain for the Heisenberg spin 1 antiferromagnet. So you see, so basically these are the largest singular value. These are smaller, and you see that there's all these kind of degeneracies that reflect the fact that this is the ground state, the unique ground state of a system with an SO3 symmetry, and indeed these multiplicities kind of reflect somehow the dimensions of the EREPs that kind of are represented in the entanglement degrees of freedom. So the entanglement spectrum reflects the symmetry in the system. But it's clear that whenever you see something with lots of degeneracies, it means that there's some information that is redundant. Okay? Because if you have things that are equal, there must be some redundant information in the parameterization of this matrix product state using such a wave function. Okay? Because there's things that are equal to each other, so there must be some hidden symmetries. Okay? So indeed, so the question that we asked and that motivated lots of these developments that I will talk about is basically the question of what is the optimal compression? So how do you identify actually the real variational degrees of freedom in these tensor networks for simulating your quantum spin system such that all these degeneracies are taken into account by maybe some topological features? Okay, and what is precisely the symmetries that lies at the origin of all these degeneracies? And much more important even, because at the end, if you look at a quantum spin system and the ground states, is not just the ground state is at the end the vacuum, the emptiness. It's completely empty. No? There's nothing there. What you want to see is to probe excitations. You want to understand what is the nature of the elementary excitations. Okay? Like if you have a symmetry broken phase, and typically elementary excitations are domain walls. How do they look like? How can you parameterize them? How can you understand them? And it turns out that for kind of non-trivial phases, this is very complicated. It's very complicated to understand the nature of the elementary excitations in a quantum spin system. And indeed, it turns out that using somehow this whole idea of this manifold of matrix product states there's also holds in higher dimensions, it's actually, there's a very natural way of defining excitation. So you find maybe your variational minimum in the energy on that manifold, and there's a very natural subspace of your Hilbert space that you can associate to this. You can kind of look at the tangent space on that kind of field. So you have this manifold, it's called the ground state. You found your minimum, and then you basically look at the tangent plane on that manifold, project your full Hamiltonian on that manifold, and then it turns out that this gives you a Hilbert space on which you can build your excitations. And this is the way you have to understand elementary excitations in gapped quantum spin systems. They can all be represented like this, and actually we have kind of proofs by which you can do this. And you see this is basically, you have like these blue dots would be the ground state, these red dots would maybe an other ground state, because of course you can have symmetry breaking, so that means that you can have a domain wall that interpolates between two different ground states. Of course, it could be that these blue and the red ones are the same if you have a unique ground state. But it turns out that all the excitations can be very well modeled like this. And just to give you evidence for this, one of the first things we tried to do this is, for example, calculating the Haldane gap. Okay, the Haldane gap is the gap, the spin 1 Heisenberg model. You kind of variationally kind of optimize these matrix product states of this, and you see you basically get this gap with kind of arbitrary precision. So this is like absolutely amazing how kind of well this works. And you can also look at these domain walls. So for example, if you look at the spin 1 XXZ model, there's many different phases, and depending on somehow the phase in which you are, you get all these very complicated king states. Okay, so these states that have a symmetry broken phase, and you can interpolate between these different ground states, and these domain walls have a very complicated structure, and you can actually look at the dispersion relations as a function of the momentum of these things. And you can also start scattering these excitations. You can say, what happens if I have two excitations, and let me kind of calculate the S matrix for these excitations. All of these things are included. For this, you need basically the double tangent plane. Okay, you need two tangent planes. Okay, but anyway, the question is, yes? No, this is not the entanglement spectrum. This is the real spectrum.
In the previous slide, in the last slide. So that one is for the XZ chain without SU2 symmetry, or with SU2?
This is the Heisenberg spin 1.
Heisenberg, so has SU2.
So it's with an SO3 symmetry.
Yeah, SO3, okay.
Indeed. And you can see that all the multiplets, well, it's actually the Heisenberg spin 1 is indeed in an SPT phase, and that's why you see somehow that the multiplets are actually half integer. Okay, that's because this is an SPT phase, so it should be indeed. You have, like on the virtual level, you transform according to the half integer representation, the projective representation of your SO3 symmetry. Okay, but anyway, but this is a problem that we had for a long time. So for the most general case, it's very complicated to understand the structure of the excitations. How do they look like? How do they fuse? How do you model them even? And it turns out that we solved somehow both of these problems, like how do you find the most efficient parameterization of ground states, and how do you actually kind of look at the nature of the elementary excitation by looking at dualities or gauging, like high energy people call it. So basically for the rest of the talk, what I will try to do is to explain somehow the following phrase, that for every model in the phase diagram of a family of spin chains with a given, possibly non-invertible symmetry, there's always a unique dual Hamiltonian where all physical and topological entanglement dual symmetries are broken. Okay? This is the optimal compressed description, and all the excitations in that optimal dual theory are domain wall excitations. That's the elementary ones. Okay? And it will turn out that you will be able to kind of model then everything in the original model by acting with the duality transformation on that optimal model, and that will give you somehow all the complexities. And this duality transformation will also be something that can be represented in terms of matrix product operators. Anyway, so what is the physics? Okay, it turns out that for doing this, I really did not want to kind of do this because the mathematics is way above my pay grade by modules, but my students convinced me that it is actually kind of very interesting. That's exactly what we need to do to understand somehow tensor networks. Turns out that we need by modules. Okay, and what you need to understand somehow these questions that I talked about is basically some kind of some commutative diagram type of thing of bimodules. So basically I have 3 bimodules that will completely specify the structure and the phases of all possible quantum spin systems. So basically I have some symmetries, that will be a category C, of course this could be our group. Then I have some kind of way of representing them, the kinematics in terms of a module, and I have some kind of an algebra, some kind of another fusion category that will control the way somehow your local symmetric observables kind of form an algebra, how they multiply with each other, okay, the local terms of your Hamiltonian. So this is the Hamiltonian. Okay, depending on the symmetry, you can break somehow a phase in different ways. Okay, so again, I'm thinking about this particular case. I'm thinking about quantum spin systems. So phase diagrams only make sense if you impose some symmetries. Okay, and therefore I look at the family of Hamiltonians with a given symmetry and all the different ways in which I can break a categorical or a normal kind of global symmetry turns out to be also labeled by a bimodule. Okay? There's also a module. All the possible modules that are compatible with a certain fusion category are in one-to-one correspondent with the different labels of the different phases. And if you start doing this, then okay, you have a module of this category. Then it turns out that there's also a dual, a Morita dual, and this will be the fusion category that controls the excitations in the system. It will control somehow how all these excitations fuse, how all the elementary excitations in your theory fuse with each other, and somehow how, well, the F symbols are related to all kind of interesting properties. But it turns out that if you have a bimodule like this and a bimodule like this, and also this algebra, okay, the thing that controls somehow the eigenvalues, this controls completely the eigenvalues of your Hamiltonian. This controls the quasi-particles. It turns out that this module is completely fixed. Okay, so if you fix this branch and this branch, then also this branch is fixed. And this kind of controls the entanglement degrees of freedom. So the entanglement degrees of freedom are another module. Okay, so this is another module. Namely, you can find a bimodule that the bond algebra, the quasi-particles, and somehow this kind of thing. So this is this Q which controls somehow the entanglement degrees of freedom. Just to make this a little bit more clear for people that know about groups. So if you have groups, then typically the typical situation is to have like a global group symmetry, and which that this category is VEC of G. My Hilbert space is a tensor product structure, has a tensor product structure. That means that I choose for this module to be only have one object, and then somehow my Hamiltonians are kind of determined by the E-reps of my theory. And then it turns out that all the different ways in which you can break the symmetry are looking at all possible cosets of subgroups and looking at all possible cocycles that correspond to this. And then you can work out, it's well known, you can find this in any book on category theory, what is somehow the dual category, and this will turn out to be the labels of the quasi-particle excitation. So you see that this is a pretty complicated thing. This is the way these excitations of your theory will fuse. And it turns out that the entanglement degrees of freedom will kind of be related to somehow this projective representations of the subgroup that you did not break. Okay, so in particular, if you do this for the Ising model, this would be like VEC Z2, VEC and Rep Z2. This would just be the Ising model. And then there's two possible phases. Okay, so either you are in the ferromagnet, okay, which breaks the symmetry, and that means that basically the excitations are given by the domain walls, or you kind of do not break the symmetry. That means that there's only one object in the phase. So this is basically VEC. That means that there's only one ground state, and then the excitations are labeled by the magnon. The magnons in your theory are basically labeled by the E-reps of Z2. Okay, so let's kind of try to kind of work this out in more detail. So let's first kind of focus on this first this first bimodule, the symmetry, kinematics, and bond algebra. Okay, so it turns out that for all these generalized symmetries for one-dimensional quantum spin systems, it turns out that you can find matrix product operator representations of these fusion categories. It means that you can find tensors, and these are other kind of, these are just tensor networks, and if you contract this tensor network, this gives me a representation of somehow a matrix of a fusion category given by these constants. And it turns out that this n alpha beta gamma, of course, has to be independent of the size of this thing. So that means that these NPOs have some topological feature. And as far as I understand, the first time these objects appeared was in a paper of Wang and his collaborators. And starting in 2014, we realized that actually all these operators can be represented in terms of matrix product operators, and we kind of started developing the whole theory, namely the representation theory of somehow all possible non-invertible symmetries. And what is crucial in this whole study is that somehow if you multiply two of these MPOs, there's something like a fundamental theorem that tells you that there's some generalized Clebsch-Gordon coefficient. If this product of these two is equal to this one, then there must be some Clebsch-Gordon coefficient that you can pull through that basically kind of intertwines the product of these two to this other one. Okay, because when it's a bimodule, you can also actually, turns out that you also have like a coproduct you can do to the other side. If this is times this is this, then there must also be a completely different type of Clebsch-Gordon coefficient that if you multiply these two, it also gives rise to this one. And if you work this out in complete detail, it turns out that you end up with this bimodule that was beautifully introduced in somehow one of the previous talks. Namely, so basically you have all these matrix product operator, the full set of all possible matrix product operator representations of a fusion category is given by a bimodule, and these MPO symmetries have like 3 or have 6 labels. Okay, so basically C is an element of your symmetry, D is an element of your dual symmetry, and that's why this D basically labels the Hilbert space, and these M's are the modules. And you see, if this M is equal to VEC, then basically there's only one element, then you will have a tensor product structure. But if M is not equal to VEC, then basically you have some non-trivial fusion rules here, and then you have a constrained Hilbert space. Okay. So turns out if you worked out all these things, these Clebsch-Gordon coefficients are related to some F symbols, and turns out that if you kind of work all these things, write down all the equations that these F symbols have to satisfy, you end up with equations that are completely equivalent to equations that we found in a paper of Alexei Kitaev and Yang Kong. Okay? Although the way they derive this or obtain this is a completely different way. From the physics point of view, this is a completely different problem, but it turns out that you get exactly the same structure. Okay? That's why you get these bimodules. And we figured this out basically after talking with Jürgen Fuchs and Christoph Schweiger, that this is the most general way in which you can write down MPO symmetries. Okay, so what is crucial in the whole story of these bimodules is that, of course, you can start now trying to find Hamiltonians that commute with these symmetries. Okay, and you know that the Wigner-Eckert theorem basically tells you that whenever you have a symmetry, then all operators that commute with that symmetry can be written in terms of Clebsch-Gordon coefficients. Okay, and it turns out that here it's exactly the same. So this is something that we proved more recently. So it turns out that all operators that commute with these generalized symmetries can be built out of these Clebsch-Gordon coefficients that we kind of wrote down. Okay, that means that all Hamiltonians, nearest neighbor Hamiltonians are like this, but of course I can also have next nearest neighbor, next nearest neighbor. It doesn't really matter. If you have a Hamiltonian that is a sum of local terms of this kind, then the eigenvalues of this Hamiltonian are completely determined by the structure constants of the algebra spanned by these objects. And now it becomes really interesting, because if you kind of look at the algebra spanned by these kind of structure constants, you see that the way they multiply with each other, your local Hamiltonian terms, again, so for the Heisenberg model, this would just be the projection on the singlet, for example. This is like one of these Clebsch-Gordon coefficients. But of course, this works now for general, for all these constrained Hilbert spaces. And what you see is that the structure constant of this algebra only depends on the 4 F symbols, and these are the fusion, these are basically the F symbols of the category D. They're completely independent of the choice of module. Okay, so again, maybe I should show this model again. So we have, what is this? Well, okay, let's go. So we have this symmetry. We have somehow this dual bimodule that determines the Hilbert space. But what we just saw is that the eigenvalues of Hamiltonian defined basically in terms of the Clebsch-Gordon coefficients, which are the skeletal data associated to this MD. This Hamiltonian will exactly have the same eigenvalues if I change this module into another module. Okay, because the eigenvalues only depend on the F symbols of D, not on the choice of N. Okay, so that means that any kind of two dual Hamiltonians that I can construct with different modules, but the same kind of constants for my symmetry will kind of have exactly the same spectrum. Okay, and it turns out that you can kind of go this further. You can now try to look at this triangle, and this triangle kind of gives you an explicit matrix product operator that intertwines somehow your Hilbert space with a certain module M to a certain module M. Okay, so this is this Mn, so you have to kind of calculate the functor, and then there's this kind of P that comes out of this, which is effectively somehow if you kind of look, fix D, you go from M to N, then there's some kind of a functor that gives you P, and P is basically exactly controlling the phase of your theory. Okay, and it turns out that the labels of this category P, okay, so as I said, this P kind of labels maybe the phases, but anyway, this P, the number of simple objects in P, will kind of tell you how many different ground states you have in that different phase. Yeah. And if you kind of work this out, turns out that all known dualities, like Jordan-Wigner, Kramers-Van Kennedy, Tazaki, but of course also non-abelian ones, non-trivial ones, all of them can be kind of constructed in this general framework in terms of these MPOs. So this is basically the thing that we did in 21. So what is interesting is that it means that you get lots of duality transformations. So it's not just one duality transformation, you get, yes, sorry.
Can you go to the previous slide? I'm a little bit curious about your Jordan-Wigner. statement.
Yes, for this you need.
Don't you need some super?
Yes, for this you need some graded vector spaces, but there's no problem. This has been done in the language of tensor networks. You can actually work with graded tensor networks, and everything works out.
Okay.
And actually, yeah, and actually also in higher dimensions, these things give rise to the two-dimensional Jordan-Wigner and all this. Yeah. Anyway, so it means that these duality transformations that interpolate between these two different modules, Q and R here, somehow there's many duality transformations, and all these duality transformations can be converted into each other by either acting with your dual symmetry or with your original symmetry. And that's why this P is a bimodule. You can act with C on P or with C star P on P, from down or up, and this changes the labels in this P. Okay, and that's why there's not just one duality NPO, there's many duality NPOs. Okay, so turns out that you have to be very careful with boundary conditions. Okay, so if you look at this, there's this amazing song on this album here, careful with that X Eugene, and Eugene is of course Eugene Wigner. Turns out that if you look at the mirror, all these different there's 4 different sectors, and all these sectors are always permuted. Okay, so it's exactly what we need for this thing. So people that know about boundary conditions and topological sectors, they will immediately recognize that there's a problem. And it turns out that in terms of tensor networks, there is not really a problem. All the possible boundary conditions for all these duality transformations are in one-to-one correspondence with tuple algebras, and then the duality transformations are ones that basically are related to ladder algebras that kind of start permuting all these different sectors. Okay, and this is something that we worked out in complete detail in a paper 2 years ago, and it turns out that indeed, if you lift somehow these tubes and you make physical degrees of freedom of all these extra legs that control the boundary conditions, then it turns out that all these transformations, all these non-invertible symmetries become actually invertible. Okay, in some sense, it's kind of a bit of a misnomer. So it means that actually invertible symmetries, non-invertible symmetries are invertible if you lift the boundary conditions to actual physical degrees of freedom. Okay, but let's, time goes fast, I see, so let's actually move to another side of the triangle. Okay, so we have the symmetry, the phase, the quasi-particles. So what does that mean? Okay, so given a family of spin chains with a generalized symmetry C, then the possible phases are labeled by the possible modules. Okay, so we have a C, then all the possible phases. I have a phase diagram, and the different phases in my phase diagram correspond to different modules P. Okay, and it turns out that the number of objects in P label the number of ground states, and then there's a dual, some Morita dual of C of P. This labels somehow the excitations, but I will come back to this. But what is important, so I have C, R, and D. This is basically fixed by the representation, by my Hamiltonian. This is defined on a certain Hilbert space. This fixes C, R, D. The P is something physical. Okay, it depends on where you are in your phase diagram. You will have a different P, but once this is fixed and this is fixed, Q is fixed exactly again by some factor. Okay, because if you fix this and this, there's no freedom anymore for this Q. Okay, so this brings me to this third axis. So bond algebra, entanglement, quasi-particles, this D, Q, and E. And it turns out that indeed, to find the ground state of a certain Hamiltonian in a certain phase, you need exactly to know what this Q is, and you have to define your matrix product state in this dual Hilbert space with the degrees of freedom Q. Okay? And then actually the ground state in your original theory is obtained by looking at this MPS and multiplying it with your duality intertwiner, and that maps it to the original ground state. And it turns out that this MPS defined on these degrees of freedom is of course the ground state of a dual Hamiltonian that is uniquely determined by basically your phase, but turns out, not at all by your Hilbert space. It will be completely determined basically by this E. Okay, so let me give you a little bit more details here. So it turns out that doing a duality transformation, okay, so if we start with somehow a certain spin chain and a certain phase, there's a dual Hamiltonian, exactly in the sense that I talked about before, in which somehow I can change these 3 letters. Okay, so this I keep fixed, but I can change these 3. And as I said, the number of simple objects in P labels the number of ground states I have in my system. And if you want to have the simplest way of representing a matrix product state in a certain phase, you want that all the symmetries are broken. So you want basically to have the maximal possible amount of ground states. So you want to put an object here, a module, that has as many simple objects as possible. That means that you want to take the choice that this module is equal to that thing, because that's certainly the module that always has the maximum number of objects. Okay, and that is the dual Hamiltonian that basically gives you the optimal compression. Okay, so there's no redundancy anymore. Like say a certain multiplet with a certain weight in your spectrum is replaced by something with only one singular value whose weight is exactly the same as the sum of all these other kind of things. Okay, so the whole structure then of the original system is I take this optimal MPS, I multiply with this kind of intertwiner, and then I have, of course, these symmetries that I can put there, and this kind of allows me to understand all the possible ground states. Now I want to go back to the other question I wanted to ask. What are the possible excitations? How do somehow my excitations in my theory look like? Okay, so we have this kind of symmetry phase quasi-particles. It turns out that to understand quasi-particles, you basically have to look at the way I labeled these matrix product states using somehow these different kind of weights. The way I do it with MPS. Turns out that if you have your MPS, then you can actually put another object B here, and you can put this dual fusion category of C. You can put this E here, and this E ends on this kind of duality label P. So that means that if this E has an action on this P, so if this P label is something, the P label on the other side will be something else. Okay, so that means that this is exactly kind of one of these domain wall excitations. Okay, and it turns out that in this optimal dual one, because all the symmetries are broken, somehow the optimal dual excitations are all domain walls. Okay, because I have the number of ground states is equal to somehow the number of labels in my dual symmetry. And what I have is that my optimal excitations are just domain walls, just like what happens in the Ising model in the symmetry broken phase. I have all the zeros and all ones, and this kind of happens in this whole phase. And using somehow this picture now, we have a complete understanding of the excitations in our original kind of theory. What this tells us actually that a very natural way of labeling the different phases of matter is actually by looking at these excitations, the fusion category of excitations, because this fusion category of excitations is something that is completely independent of which dual model you are looking at. Okay? Because this is where the physics is. You want to understand excitation, the spectrum, somehow the way the spectrum will look like, expectation values, all the contents that you can calculate with observables, of course, depends on how the excitations look like in your system, because the vacuum is just very boring. You want excitations. So all dual models have exactly, if you're in a certain phase, somehow the meaning of these phases is very different, but somehow the excitations are the same in all different labels. So that means that you have basically all these phase diagrams should in some sense, in a very natural way, be labeled by the fusion category of the excitations. And that's something that's completely independent of the duality or the dual Hamiltonians that you take. Okay, and that now kind of poses an extremely interesting question that I would love somehow to discuss with some people. It turns out that, of course, what happens at the phase transition between these two kind of different phases, if I kind of continuously go to this, I have two Morita equivalent categories that label the excitation, the fusion rules of the excitation in these two theories. So there's a very natural bimodule that I can associate to any one of these things. So what does that have to do with somehow the CFT or maybe the first order phase transition or the constriction? Maybe there is no, you don't know beforehand, is it the first, the second order? What are the conditions that somehow these fusion categories of excitations give? In the last minutes, okay, this might sound all kind of very kind of theoretical and you say, okay, can you kind of show that this works? And indeed, this is exactly what we did in that paper. We kind of developed a DMRG for these modules. Okay, so we have to kind of really rethink the whole of these tensor network models because you have to work on Hilbert spaces with constraints. Okay, so as I said, somehow you don't have tensor product structures anymore. Even if you start with the Hamiltonian with the tensor product structure, the optimal dual one might well be a gauge theory with kind of constraints. And somehow this is what we did. We looked at an interesting Hamiltonian with an A4 symmetry because this is kind of an interesting one. And you look, for example, if you're in the A4 SPT phase, it turns out that there's exactly 7 dual models. You can do DMRG for these 7 models and look at the entanglement spectrum, and you clearly see that in this A4 SPT, that this is the one that has somehow this is the most efficient representation. You also can just measure how many bits do I need to represent the ground state, and clearly somehow there is indeed a way of choosing a dual model where somehow there's no information, there's no degeneracy anymore in your entanglement degrees of freedom. Okay, do the same thing in another phase, you again kind of see that, okay, the A4 symmetric phase, immediately this is the optimal one. Okay, turns out that this is the case. You can also do this for all these kind of cases. I think there's also some extremely, from my point of view at least, very interesting physics story about this. Okay, so it means that for every Hamiltonian, there's a unique dual one with the same spectrum, but which is completely symmetry broken with respect to its dual symmetry. Okay, and this is the one you want to simulate, and it can actually yield kind of a huge simplification in these things. And it also kind of solves this whole puzzle of what are the possible excitations in your theory. And in many ways, this generalizes this famous Kennedy-Tasaki transformations to arbitrary categorical symmetries. So it turns out that you can even do this for continuous groups. Okay, so I think the purist categorical people will heavily complain that you cannot kind of associate categories to a continuous group. Because, okay, but nevertheless, it works. Okay, you just write down these tensor networks. And what is extremely interesting is that there's, of course, these Merman-Wagner type of theorems that tell you that continuous symmetries cannot be broken. But you can actually kind of go to a dual theory, which does not have any continuous symmetries, but have these kind of symmetries that are governed by the E-reps of your Lie group. And there's no Merman-Wagner theorem for those. And this is exactly what happens if you want to study something like the Heisenberg model. Instead, you study something like an interaction around the phase model that has a categorical symmetry, and in the ground state, all these symmetries are broken, and therefore there's a much more efficient way of representing them than the original model. And this is, so in the, let's say, last minute, I have 1 minute left, I just want to go back to this discussion that in all the conferences have been when people talk about generalized symmetries, there's always this confusion about gauging versus dualities. And I think actually this triangle gives possibly a solution to that kind of riddle. Okay, so basically the way I have looked at this, the thing that we did in this talk is I have some kind of this bimodal that completely, that hopefully you understand, kind of really gives all the physics of this quantum spin chain in a certain phase. And by the dualities, you basically keep this D, Q, and E fixed, and you change these three labels. That's a duality transformation. That's a very non-local transformation that turns out to be linear depth. Okay? But there's something different that you can do. Okay? So what you can do is instead of changing somehow, keeping this fixed, you can also basically keep this fixed and only change the representation of your kind of system. Okay? What you can change is your Hilbert space. And it turns out that this change, if we go from an RD to an R prime D prime, this can be done with a constant depth quantum circuit. Okay? So this is a basis change. And as far as I understand, this might be what people in high energy physics call a duality, and that might be gauging. Okay? And if you kind of look at what you could do is something like the Kramers-Wanier or the Joyner-Wigner, it turns out that it's a combination of the two. You actually do both. If you look at Kramers-Wanier, the way it's defined, it's actually both doing this, and therefore you kind of go to this. There's two possible paths to do this. Anyway, I have to stop here. So these are the references. Thanks for your attention.
Imagine you in 2+1D, you would say the same. You would go to the maximally, yes, so the SSB phase, yeah, and model that. But in that case, there can be instances like in Louisa's talk that you have sort of braided fusion category, symmetry, degrees of freedom. So is it still optimal to model this one? So it's much more, it's much more subtle in 2D because there is this famous Elitzur's theorem that tells you that you cannot break one-form symmetries spontaneously. Okay, so basically the symmetries that you will break are the global symmetries, and you're still kind of investigating exactly what happens. So, but it's still clear all these dualities actually work also in 2D, but this whole notion that every phase is equivalent to something that breaks all dual symmetries is certainly not true, because these dual symmetries, if they are gauge symmetries, like one-form symmetries, they cannot be broken spontaneously. Again, we are still kind of investigating exactly what is going on there. Yeah. From a fusion 2 category point of view, it's the same. They're bimodules. Then you can the math is the same, but the physical interpretation is different. Yes, but yeah, I think you would get additional topological order, which will obstruct it.
So along the lines of the question that I asked yesterday morning, in your A4 model, you have essentially 12 different kinds of domain walls, right? Because A4, it's 24 factorial, or sorry, it's 6 factorial divided by 2, or 4 factorial divided by 2. So there are kink operators or domain wall operators for each of those.
Yeah.
Now my question yesterday is, I'll rephrase it and ask you, do those have local commutation relations?
Yes, so So all of these domain walls, well, it's effectively exactly the same as what happens with the Ising model. No? So it doesn't really matter whether it's A4 or not.
For the Ising model, they will, but for this case, you have a non-abelian group. So if each one corresponds to a different half global rotation of A4.
Yeah, but you can look at how they fuse, and they will actually kind of govern the category like is given by this fusion category. So there is not really. So they commute. Of course they don't commute because do domain wall here and one there, they will kind of overlap, no? And
exactly.
And they
so
don't
they overlap.
Commute.
So what's the answer? Do they commute or do they not commute?
No, I don't think they commute.
Okay, thank you.
If you know the entanglement spectrum in one formulation, is there a simple way of figuring out the entanglement spectrum in the
yes.
world?
No, it's indeed. So this is exactly what I tried to do in this picture. Okay, ignore this C and this CP star, these are the symmetries. This is the optimal compressed MPS. And the MPS in your original theory is basically this one times this intertwiner. So all the degeneracies in your entanglement spectrum originate from that intertwiner. Okay, so that's the one. So this, of course, this times this is also an MPS. Okay, and basically the degeneracies in your MPS, on your entanglement spectrum, completely come from this topological term, namely the MPO intertwiner. Okay, and that clarifies basically everything, also for the spin 1 Heisenberg. For this, you have to go to this continuous group, but somehow this is the way to understand, this is a different way in which you can understand somehow entanglement spectra. And also, like, of course, Kennedy-Tazaki, for example, turns out that in this particular case, this Kennedy-Tazaki, this MPO is bond dimension 2. So it will take basically effectively any kind of ground state that you have in that phase with a certain singular values, and it will just double all of those.
Okay, thanks.
Well, double of those such that the weight remains the same. No? So that's important. So the total, of course, both of these systems are normalized. So basically what you take is one eigenvalue and replace it with two eigenvalues that are half of it. Or in general, somehow, this is another formula. Turns out that for more complicated groups, like quantum groups, you can also do that, and you can split one eigenvalue in different ones, and these different ones don't have to be equal to each other. Okay, so there's actually very interesting situations that can happen.
Can you go back to the slide of duality engaging?
Yes. Again, it's a conjecture. No?
Things you ask. So I think for finite depth circuit, I would say it's more like adding a local counterturn in the field theory context. It's more like a trivial duality. And for gauging, I don't think it's literally the same as a linear depth circuit. Globally, if you work on a closed circle with periodic boundary, with a fixed boundary condition, linear depth unitary cannot implement gauging. You have to multiply it by a projection.
No. Okay, but again, if you kind of take the boundary conditions into account, it is actually a linear depth
If you allow yourself to
and I allow this because I did this in my talk. I did this in my talk before. But I agree. But effectively, I'm just it's non-constant depth. Okay, then it's just something that is topological, something that maps a local to a non-local thing, so it cannot be a local circuit. Okay, but it's interesting that changing this bimodal is completely local. Okay, you can actually do this in a depth 2 circuit.
Yeah, I would say that's more like adding local counterturns, or at most a trivial.
No, but that would exactly correspond in the Kramers-Wannier discussion to the Hadamard transformation that Nat talked about yesterday. This is exactly something like this.
Let me put differently. I don't think it covers all the possible.
No, maybe not. But at least you see that there's two very different. At least there is already some possible path of resolving this in a mathematical way.
It has the right flavor.
Just following up on this, you had the example for the Ising, the Z2 transitions, right? The SSB and the trivial phase, your triangle diagrams. And there basically, I wouldn't say you go from, exactly here. So changing the VAC Z2 to VAC on the
this is the phase. No,
northwest to southeast diagonal. I don't think we should think of as gauging. It's more like changing the physics. Like
no. This is not gauging at all. This is just.
This is not gauging.
I define a Hilbert space, and I'm just looking at what is the right
because
triangle
in your other diagram, R prime also
in that phase. And the Ising ferromagnet, this phase is VAC Z2, and P here is VAC. That's the way to think. But I'm not gauging here at all. I'm just saying this is the way of understanding the physics of the quantum Ising ferromagnet. And this is the way you can understand the Ising paramagnet. And similar way you can understand any phase of a quantum spin chain using somehow this bimodule.
So gauging here would be changing the vector?
Gauging would be keeping basically this thing and changing these three things. That's gauging.
Yeah, I think we can put a discussion after this. I think there's one last question, and then that's it.
Oh, I just wanted to hear your thoughts on the gapless, on the critical point between the two phases. So you're considering gap phases here
yes.
with quasi-particles, right? So I would imagine at the critical point, you lose the quasi-particles generically. So why do you expect the categories that describe the gap quasi-particles could still be used for the gapless point?
Because they are kind of this, there's a fusion category here, there's a fusion category here, they're Morita equivalent. Mm-hmm. I can define a bimodule. Maybe it might contain some information about the CFT. I have no idea. It's a conjecture again.
Thanks.
Let's thank Frank.